Discuss at your table what's going to happen to a person who tries to rotate while on a chair without touching anything outside. Obviously, this has to be a chair that has wheels, or you could use my fancy machine right here. So, without touching anything outside, so like this, could a person move their chair? Talk at your table.
Lower and upper body. Like move your leg away the way you move your upper body the other way.
I don't know.
That's exactly what it is.
What happens to the person?
You have to use air resistance.
All right.
This is what she's doing. Easy peasy.
That's outside force.
No, it's not.
Watch me.
Is it considered air rotation?
Oh,
Dad.
Ugh. Why did I really not move?
What are you going to place the equal and opposite force on?
What?
The equal and opposite force. Where would it go?
Like how I'm doing pretty much the same thing in both directions?
Yeah.
Yeah, like, couldn't move. Wait, what if you just did this?
You can't even.
Wait, you're moving now.
I know, I pushed off the floor.
But she
Wait, hold up,
continue
stop.
moving like forever.
What if you just do it in one direction? No. You only dab in like one direction. Like you go like that, and then that, and that. Exactly. You can move.
Okay. So nothing really happens, and this is why. There's no net torque. There's no angular acceleration. If I wanted to move, if I wanted to spin, I'd push off the floor and be like, wee! Okay, but there's no net torque. Also, I'm recording this, so you get to listen to that later. So if there's no net torque, there's going to be no change in acceleration. I already did this for you. Now check this girl out. Watch what she's doing.
wow.
Yeah.
No, it's a simulation.
No, I think it's a photo.
Now, focus.
That's savage.
Watch her motion.
Yeah, no, this is an ice rink, not a lake.
Stop. Okay, besides the fact that this is just funny, there's actual physics happening here. So what is she changing about her motion?
She's changing the shape of her body.
Yeah, she goes more and more like up, like vertical.
She's going more and more.
Streamlined.
She's streamlining her body, and then as a result, what else happens?
Her inertia, the rotational inertia decreases, and her
Velocity
acceleration increases.
Yeah, so she's going faster and faster, right?
Yeah.
Okay, and she's doing that by changing her rotational inertia, by pulling her body in. Okay, so how did her rotational inertia change? I think a lot of you have already said this, so write that down. Oh my god. So Sarah, how did her rotational inertia change?
Changing the shape of her body,
Yeah, it got smaller. She's changing the shape of her body. She pulled in her mass closer to the pivot point. Where's the pivot point? Like this?
Oh, it's on her foot.
Where's the rotational axis on her body? Cut like this?
No, through her head.
Like this, right? If I start between my feet and then make an imaginary line up through the top of my head, that's my axis of rotation. So she starts out something like this, yes? And then reels it all in like this. How did her angular speed change? Yeah, she was getting faster and faster. So fast that she was able to break through the the ice. Ha! Definitely not.
Oh, she died.
Okay,
Ice is
you're
water.
okay. You know what it should be. The answer's in your brain.
Hey, they can have a
It's in my heart. It's not work.
Hey, so what do we need to do in order to be able to get our quizzes back today?
Focus.
Focus, transition, not throw erasers at our table mates.
One of those things, not like the other two.
Okay, write Newton's second law of rotation. What is it?
It's rotation.
T equals to IR. I alpha.
Net torque equals I alpha. So rotational inertia decrease and angular acceleration increase. That makes sense, right?
Yeah.
Yeah, okay. But what was her net torque?
Oh yeah.
It is the same.
She's applying the same force the entire time?
No.
There's no forces applying.
When does she apply a force that creates rotation?
At the start.
She initially pushes off like this, right? Then when she does this, what torque does she apply?
Nothing.
Friction?
On ice. Nothing.
Air friction.
Nothing. Nothing. She pushes off. That creates the torque to allow her to spin. Then she reels it in like this and spins faster. But when she goes from here to here, does she have a torque?
No.
No. So there's no net torque. All right. So now we're saying 0 equals increase, decrease.
Is the inertial zero?
That does not make sense, right? How can we have a change in rotational inertia and a change in acceleration without any torque? How do you know? We have nothing to prove this.
Hey,
What does this mean?
Mr. Chan.
What do you need to do? 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 Okay, so if we start looking at this, we basically just proved net torque equals I alpha. We have 0 equals stuff. Can 0 equal stuff?
No.
No. So what needs to be true in order for us to continue using net torque? How did we break this?
There needs to be forces.
Energy.
What broke it? Why can't we use net torque?
Zero equals.
What did the skater do that broke it?
Oh,
She didn't apply a torque.
Well, what else?
she used.
Oh,
she used
Raise the arms.
And what did that do?
It changed the distribution of mass.
She changed her eye.
That's literally what it is.
Oh,
So in order for this to work, what do you need to do?
change your eye.
Change your.
No, we just changed I and we broke it.
Make torque
My eyes
0.
don't change.
If we change I, we broke it. So how can we still use net torque equation?
The I must stay constant.
I must stay constant.
I isn't constant.
Yes, that's what today is all about. So let's break it down. Wicka wicka. All right, we're going to look at these side by side. Before, a long, long time ago, we talked about Newton's second law, F net equals ma. And we said that we could think about this in a different way. What is acceleration?
Delta V over T.
Delta V over T. So we plugged that in, we said, okay, cool. What causes a change in velocity? Well, a force over time. What equation is this? Impulse. So we said, okay, if we apply a force over a time, it can cause an object's velocity to change. Now, what had to be true for that to work? Alex?
Same mass.
Same mass. And that's the mass of our system. And the mass of our system is always going to stay the same. Let's think of an extreme situation. I'm standing on ice, and I say, I can break physics. I'm going to change my mass. I chop off my arm, and I throw it across the ice. What happens to my motion? A torque?
Your
A
velocity
torque?
increases that a lot.
My velocity would increase, right? So I've thrown my arm across the ice, my arm is moving, and then my body starts to move, right?
Yeah.
Have I changed my mass?
No.
Wait, what?
Yeah.
If I walk off the ice,
The system's mass hasn't changed.
Wait, what do you mean?
But you're.
chop off my arm, throw my arm, what happens to me? I move, what's in the system?
Arm and the body.
Arm and the body.
Oh god.
This is pretty much.
So even though I chop my arm off and when I walk away from this, first of all, I'll be bleeding excessively and I will no longer have an arm, the arm never left the system.
So it's like this collision problem.
Oh! What unit are we thinking back to? Momentum.
Wait, so this is question 6. What is it?
Not yet. All right, so if we were thinking the same thing, then we'd say alpha is the change in omega over time. So we'd write like this, and then get to here. What kind of equation do you think this is now?
Angular rotational momentum.
Well, what was...
Momentous torque. I don't know.
What are you saying?
Momentous torque.
What was this one?
Impulse.
Impulse. So what do you think this one is?
Torcular impulse. Impulsive torque.
Angular momentum.
What was this one? What is this one?
Impulse.
Rotational impulse. Now, I'm going to tell you that using rotational impulse isn't always super useful to us. Because what this equation is telling us is torque exerted over time causes an object to change its angular velocity. But what was the situation we just talked about with the figure skater? Was she exerting torque over time?
No.
No. So that's not going to be super helpful to us. We need to think about this a different way. Because this statement is only true if I is constant. Look. We're saying if omega changes, then that means we're exerting some kind of torque over time. But what part of this are we ignoring? Alex?
The angular velocity. No, never mind.
No, I just talked about the angular velocity.
The time.
For our figure skater, this doesn't work.
Oh.
Because her omega is changing, but there's no torque. So what part of this do we need to think more about? The I. So instead, we need to put our delta out here. Because it's not just omega that can change. I can change too.
Since I is constant, it would be change 0. It would be 0.
So Devia is going places. She's ready. She's saying, well, what are we talking about with our figure skater? Which part of this equation ends up being 0? Torque. So if that's 0, and delta means what? Change in. So how could I write that?
I W final
Delta I times delta W.
Good job, Abby. Oh, darn the little hand.
Oh, the total is also the same, so it'd still be 0.
You gotta get rid of the trial version.
Better? You're fine. We just talked about angular momentum. If torque is 0, what needs to be true about angular momentum? I know you. Andre? It has to be constant. So, our change in angular momentum needs to be 0. And for our change in angular momentum to be 0, angular momentum needs to be constant. Now I'm going to introduce to you the letter we're going to use for angular momentum.
Oh.
Are you there yet? Have you figured it out?
Oh, Lanote.
L. Oh, Lanote.
I thought it was just notes for us to take some fat.
I thought it was L'Hopital's rule.
So L equals I omega.
I think I was every day.
All right, so our angular momentum needs to be conserved. Let's think about our angular momentum for our figure skater. We're going to compare the initial and final for our figure skater. What's true about her initial and final angular momentum? Was there an outside torque?
No.
Is there a change in angular momentum? No, it's the same. So if it's the same, I can write this. And then if I were to substitute in, when is her rotational inertia larger? At the beginning. How do you know?
Slower.
Her body's spread out wider. More mass distribution. Good. So relatively, I make those different sizes. What about her angular speed? It increases. Do you see how these are proportional?
I said that before.
You did say that before. Now we can explain why.
Did we do something before?
It's just like momentum. Now, what about for the tumbler in your bell ringer? I want to talk about 3 different positions that the tumbler was in. Gymnast, tumbler, bell ringer.
They didn't do the water for Twitter. Shame.
What 3 parts of the motion should we talk about, Kevin?
Before they jump.
Before they jump. Where else?
At the top.
At the top and
When I land.
when they land. So, how would you explain their angular momentum at those 3 points?
Increase, decrease.
The angular momentum?
No, it's constant.
The angular momentum is constant the entire time. What's changing?
The IW.
IW. Megan, tell me how I changes for the tumbler. It's decreasing when? So what does the initial position of the tumbler look like? Show me. The initial. Right? And then midair, what does the tumbler look like? And then finally? Right? Okay, so what changed there?
Radius.
And what did that
Mass
change?
distribution.
Mass distribution, which changes
I.
I. Okay, so when my eye is like this, big or small?
Big.
Medium.
Small.
Big.
Even bigger.
Okay? And
Around
then
there.
what about my angular momentum? Or maybe angular speed?
Increase.
Zero.
Zero.
Very fast.
Increase. Decrease.
0.
Does the tumbler want to keep moving at this point?
No.
No, because if they do this, what happens?
They lose points.
They lose points, yes? So they don't want to have to step out of it. Why do they put their arms up besides looking fabulous?
To increase their
Zach? Okay. Oops. Here we go. Yay. All right, so just like last unit, initial momentum equaled final momentum if there's no outside force. So when does initial angular momentum equal final angular momentum? I know it's not in the notes. This is for learning. When does initial angular momentum equal final angular momentum?
I is constant.
When there's no net torque. Our figure skater's eye changed, but did her angular momentum change? No. Okay, so this is not on the worksheet, and we already did it.
Wow.
I know.
Are we working ahead?
We're talking ahead. Yeah, again.
So does like all this like L stuff just apply like 0?
Yes. Well,
Again, do you think the L?
angular momentum always applies, but it doesn't change when there's no torque. Okay, I think this is where I have some cool... Oh, okay, not yet. So, 5. Why does the translational version of Newton's second law still hold true? Why does FMA still hold true? I already told you the answer to this. What, Kevin?
Because mass stays the same.
Because mass stays the same. And then how come, what can we change with rotational that we could not change with translational?
Distribution of mass.
Distribution of mass, rotational inertia. Now I get to show you cool things. No, not yet. Answer 7. But don't do 9 through 12 yet. Answer 7, but don't do 9 through 12 yet.
Inertia, but can change the system.
I say calor. Come on.
Joshua Hunt, Taylor Wilbur, Sasha Zabaraba, to Daniel Resnick, 43,100.
All right. A force internal to the system cannot change the system's what? Mass, but can change the system's I, shape and size, which changes rotational inertia. Now do 9 through 12 with your partner.
Sure.
Push the ball from right at them a little bit to one side. On the right, a lot of one side is going to be
A little bit to one side. Right at them.
When you're right
If it's over here, then they will have it over here, then you list that.
when you're right,
I think it's
the ball.
Then the system's mass.
Is this the center, right?
No, the mass change. Since the ball is not at the system, but that it's still supplying a force. The force because you're saying if the ball's in the system and the mass and it applies a force inside of it, so CBA.
What? No, I was right, it's CDA. No, it's CDA. When you throw right at it, you don't move. It's CDA.
If it hits your hand, you're like,
It's CDA. It's CDA.
exactly. Does it extend more than the stays constant used to be up here.
9 through 12. Here we go. All right, so imagine that I'm sitting here, and you're going to provide a force in those locations, right? I'm just sitting here. If you throw the ball at my chest and I catch it here, what's going to happen to me?
You're going to move back. Nothing's going to happen.
Rotationally, what's going to happen to me?
Nothing.
Nothing. Why?
Radius is
Because that's
zero.
your center of mass and my center of mass.
That's my center of mass. Right here.
Okay, the radius is zero.
If that's your peak
And
load.
there's the greatest inertia.
Actually, you will rotate but back.
You want to say that again louder?
No.
Why? It's funny. Where is this? What is this right here? Axis of rotation. So if you apply a force at the axis of rotation, will it supply a torque?
No.
No. So then when you decide, is it going to be bigger at my elbow or in my fingertips?
Finger.
Fingertips.
How do you know?
Radius is larger.
Because the inertia.
CDA.
Radius is larger.
So the I rock is
So
Carrots.
The T net is larger.
the T net is larger. So if the ball is in the system, why does this make sense? Or sorry, if the ball is not in the system, I apologize. What is the ball doing if it's not in the system?
applying an outside force.
Applying an outside force, which in rotational we call
Torque.
T-net.
torque. It's applying an outside torque. So for it to apply outside torque, it's going to be going faster over by my hand, so I'll go faster. What about if the ball is in the system? Now it's not an outside torque. Zach? Oh, so I won't move? Now that the ball's in the system, I catch it out here, I'm not going to move? Oh. What's happening? What do you think, Anne?
If you maybe move your arm forward as you catch it.
If I move my arm forward and I catch it, then nothing would happen, right? Okay, but what if I don't do that? Why does your inertia increase?
More spread out.
Your mass increase, right?
No, but it's mass already in the system.
Oh, but the mass is in the system. Oh.
That means you change the IW.
Change the velocity.
Change the velocity. What's happening here that we learned about back in momentum?
A collision.
A collision! So wait a minute. What kind of momentum does the ball have?
Ooh, perfect thing.
Inelastic.
The ball has rotational momentum?
Well, if-
What? Angular momentum's conserved, right? The ball caused the person to rotate. So the ball must have had angular momentum. What? Is it rotating though?
Yeah.
It
Wait,
could
what?
be.
Oh my God.
What if it's not though? What if I throw a solid block? How is this possible? Great question. Okay, don't let this black out.
Just tap it.
If it starts to dim.
Okay.
Shout out the home team.
Who wants to spin? Okay, they have tissue box? I feel like we get into
Wait.
it every single day.
Are you gonna catch those?
No!
Yeah.
God.
Tom Brady.
Alright, I want you to hold these in your hands. Yeah. Okay? And I'm going to spin you, and then I want you to change your
Distribution of mass.
I want you to just change something about yourself, so your angular momentum,
Like this?
so people can see things. Yeah.
That's dangerous.
Oh, shit.
Sorry. I almost fell off.
You don't want to change the slide, though. Rohit's giving you bad advice. Alright. Ready?
Yeah.